Here I'm going to talk about the applications of digital image correlation and digital volume correlation in fiber reinforced composites. And I'm going to start with some introduction and basics. And later on, I will give some examples and case studies in which these people, which are listed here, which is a quite long list, have helped me out. Let me start first with a question to you, the audience here in the room, that what do you think this picture is? Is it a micrograph of fiber reinforced material, since we all know about composites, and maybe the camera was not in focus while taking this image, or you have any other ideas? If not, then I say it myself. No, it's not a micrograph of the surface of the specimen, but it's a strain map taken at the microscale from a fiber reinforced composite using DIC. And this is normally the image that we are used to see as a result of DIC, but here I just changed it to a grayscale image. And we apply this methodology, for example, to non-engineered composites, and these studies have been done on at the microscale. We can also, as you know, look at the mesoscale structure of composites, for example, cracks in multidirectional laminates or tows in textile composites, and also, obviously, macro analysis, which is quite commonly used in the field. Okay, let me start with a brief introduction on the technique. Digital image correlation has been introduced. First, I just mentioned the outline of the presentation. I will start with the fundamentals and then a few case studies. Then I will talk briefly about quite a special application of DIC. And in the end, very brief introduction and explanation about digital volume correlation. Digital image correlation was introduced early 80s at the University of South Carolina. It's an optical technique which helps us to quantify the deformation, looking at the consecutive images taken from the surface of the deforming object, and it directly results in a strain, first displacement and then strain maps. This is how it works. The images that are taken consecutively are divided into small subsets or grids, if you would like to call it like that. And then each of these subsets has a certain type of unique speckle pattern in it, or unique gray intensity pattern. And by using this gray intensity pattern, the DIC can locate each subset in each image and then assign a displacement vector for this specific subset. So once this is done, then for, let's say, nearly each point in the image, we have one displacement vector defined. And by measuring this displacement between the positions of subsets, we can obtain displacement vectors, and then using gradient of these fields, we can obtain strain fields. Very simply and basically, so this is our specimen here. We take images of the surface of region of interest, and then by processing these images in DIC software, we obtain displacement maps and consequently strain fields. The requirement for this is a random speckle pattern on the surface. As I already mentioned, this correlation process is performed using the unique gray intensity pattern in the subsets. So this asks us to have a random speckle pattern, and this speckle pattern should not be repetitive, should have high contrast, and should be isotropic. So here in this image, you see some bad examples of a speckle pattern. How to create a speckle pattern? Well, first of all, we should look at our material surface on the scale that we want to do the analysis to check if there already exists intrinsic texture. If that's the case, then we can use the texture as a speckle pattern. But most of the times that's not the case, and we have to create a kind of artificial texture on the surface. This is done with paint spraying and more recently printing a speckle pattern and sticking it onto the surface. And for microscale, especially microscale cases, we can deposit some particles on the surface of the material, as you can see. DIC can be applied theoretically at any length scale, and this length scale is basically defined by the scale of the images that we are looking at. So first, we should see what are the features that we want to analyze with DIC. Is it a void? Is it a crack? Is it the toes inside the textile? And based on this, we can choose the scale of our analysis. And then based on this, we set the imaging scale. And finally, we have to choose the right speckle size for this type of analysis. The most basic and frequent application of DIC, as we all know, is measuring the global strain, for example, in a tensile test. So if we just put DIC cameras here, we take images during deformation. Processing the images will give us strain maps, and by using the average strain maps, for example, we can obtain the applied strain. And this is something that probably a lot of you have already done. But here in this presentation, I'm going to talk about a few, let's say, more exotic applications of DIC. And the first one is characterization of matrix or transverse cracks in multi-directional composite laminates. For example, here we have a cross-ply carbon epoxy material, and we prepare these specimens according to ASTM. So we cut them, we polish one of the edges for further processing, and we apply end taps, and also we apply a speckle pattern on one side of the specimen. In this case, we have two types of materials. One of them is reference or perfect material, and the other one is a voidy or imperfect material. This is the methodology schematic. As you can see, we take images with two cameras, two optical cameras, one of them from the surface of the specimen, the other one from this small area on the edge. And by processing the DIC strain maps, we can later obtain the crack density and crack density evolution. The results look like something like this. For a strain map at the surface view, you can see that the transverse cracks here start from the edge and span through the width of the specimen. And in order to obtain the crack density evolution, we have to count these cracks in function of time, but we can also do it using a more using a semi-automatic approach, like profiling a strain along a certain line here and detecting the peaks, for example, using MATLAB, and then plot this crack density evolution graph. This approach is obviously faster and more objective and less laborious. We can look at some of the results. As you can see in the first stages, there are a few cracks starting at the edge, and proceeding the loading, we see that the cracks span through, and at some point they somehow reach a saturation level. And since we have a 90-degree ply on the surface, we see that this saturation level is quite high, and somehow at this scale covers all the surface. We can look at the edge of the specimen, the same story, the same concept. The cracks appear here as peaks in strain profiles, and we can obtain crack density evolution for these two materials. We can also have a look and compare the two different views, the top camera and the side camera, and we see here that the results are in quite good match, and especially the initiation is very well detected by both techniques at the same time. And the mesoscale analysis seems to be slightly higher in terms of crack density. Then we needed to know more about the interaction of these transverse cracks with voids, which were the focus of this study specifically. And for that, we needed to zoom in a little bit more into the material surface and see this interaction. So we decided to perform a similar study, but inside an electron microscope. So we apply 3-point bending on the specimen, and we look at a very small region of interest here. And this is where we're going to apply DIC in order to check this interaction. And as you can see here, I don't know if it's clear in this image. Yes. So you can see the cracks here starting from the voids, the first cracks in this region of interest at least. And then gradually by applying higher levels of load, we see that the two other cracks appear at regions without voids. And then here applying DIC shows this strain localization features, which somehow validate the fact that these features correspond to the matrix cracks, as we can also see them with the naked eye, or not the naked eye, but visually. So that's about detection of cracks using DIC at different length scales. We are also performing high-speed imaging on multidirectional glass fiber epoxy material. And we can see that in a very, very short time period of 1/4 of a second, this crack forms here somewhere, not at the edge, but a little bit further from the edge, and spans through the thickness. This is an ongoing study, of course. Without application of DIC, especially for the initiation, it's not very easy to pinpoint the initiation of the crack, but DIC provides this opportunity that we can exactly, or with a high accuracy, pinpoint this initiation. This is an ongoing work, and I think Dimitro will talk about it more in his presentation on Thursday. So if you're interested, please follow. Then let's go to the microscale deformation analysis. The first image that I talked about is actually acquired via this methodology. The main idea is to develop a methodology which allows us to investigate deformation of fiber reinforced composites at the microscale, because we know that whatever happens inside the composite material is governed at the microscale. So for this, we have developed this technique, and we start with preparation of sample and speckle patterning and so on. Here in this study, as I will explain a little bit later, the main focus was on speckle patterning of our specimens. So the samples are prepared and cut to this dimension, something around 70 by 8 millimeter. And this is an image of the unspeckled, let's say, surface of the glass fiber material. As you can see, there are large areas of uniform gray intensity, which is not good for DIC. For DIC, we need to have a pattern, a random speckle pattern, and that's where the challenge started for us. So we had to apply speckle pattern here, and for that we had to choose, because as you can see, the fibers here are quite small, 17, 18 micrometers. So the speckle patterns that we had to go for had to be a nanoscale particle. For that, we chose a alumina powder, and then applying this or depositing this alumina powder on the surface of the material was not was fun, but was not easy. We decided to just deposit this particle out of a water-based suspension. So we did, the only thing that we could do was trial and error, of course, and we started with such a deposition. And as we can see, there are very large agglomerations in the speckle pattern, which is not good. It basically covers all the region of interest. So we had to use ultrasonication and steering, and later on using a dispersing agent in order to be able to disperse the particles, agglomerations, and be able to, let's say, distribute them somehow uniformly on the surface. But the concentration seems to be quite high, so we reduced it, and then we saw it's quite low, but then we decided to apply 2 times. So once we apply the deposition, then we let it dry, and again we apply another round of deposition, and in the end we could obtain such a pattern which was satisfying. In order to evaluate this pattern, your speckle pattern, there are some techniques, and what we decided to do was to digitally deform our image of the speckled material and then apply digital image correlation to this virtually or digitally deformed image. So basically we had to extend, for example, the length of this image by any image processing tool, and then apply DIC to see if this digital deformation could be detected or characterized correctly. And as you can see, for regions without a speckle, we have some, let's say, deviation in a strain, which is basically considered as an error because the deformation should be more or less uniform. So with this, we could evaluate the pattern quality, and then we had the specimen ready for the test. So we put it inside the electron microscope, and this is the whole thickness of our specimen. And this small region here is exactly where we had to look at a higher magnification. We applied loading, basically kind of interrupted loading. So we loaded up the specimen up to a certain level. We took a scanning electron micrograph, and we continued this for 60 micrographs. Here I'm going to briefly show some of the results. These are the strain maps obtained compared to the finite element model, which was based on the let's say, displacement results that we obtained with DIC. And as you can see, even the small strain localizations that are predicted with finite element could be detected also at a very small scale using microscale DIC. We also looked at the strain profiles along different regions, and we see that the results are in quite good agreement with finite element analysis. So basically, fibers have very low deformation, which is expected due to their high stiffness. The DIC results are rather noisy, and especially at the edges, we can see that there are some issues. I tried to cover those issues with putting these circles around the fibers to make it somehow looking as we want, but at the edges, we know that the DIC struggles a little bit because of the high gradient in the strain. But still, for such a small length scale, we were happy with the results. That's why we wanted to apply this methodology to a real case, or a more, let's say, useful case study, and that was nano-engineered composites. So this nano-engineered composite is a composite made of alumina fiber textiles on which carbon nanotubes are grown in form of forest, as you can see. And this carbon nanotube forest somehow induce a sort of modification to the microstructure of the material. So it is possible to look at their effects probably with this technique. So the same story, I'm not going to explain the details of the speckling and sample preparation. We just speckle this sample, put it inside electron microscope under our mini tester stage. And again, looking at this study zone and interrupted loading, we obtained some number of images on which we could apply DIC, and this is the result. So we can see that the fibers and even the CNT forest are well detected by this technique. We could even detect a debonding, or the debonding is happening around the fiber at this scale, which was something nice. Again, we compared this DIC strain maps with finite element methods, and good agreement was achieved in this case as well. And finally, for this study, we looked at the strain history of different features, including the fiber, the matrix, and the CNT forest, and also the debond. And just for the debond, we noticed that it's not really linear, the local strain versus average strain, and that's normal because here we have some propagation of this debond kind of tunneling inside the material, which creates this nonlinearity. But in the end, we could measure this small debonding and a very, let's say, tiny opening of the debonding with quite good accuracy. And finally, the last example for the normal applications of DIC, as Guillaume already talked about it a little bit, we can apply this technique in order to identify the crack tip in a DCB test, for example. And we have done this with Thanasis, who is going to talk about it in more detail also on Thursday. So please follow that one as well if you're interested. And here I want to talk about a special application of DIC, which is not for deformation analysis, but it's developed for, let's say, characterization of the microstructure. So we are interested to study or to investigate the misalignment of fibers in a UD composite. And for that, there have been different approaches developed. But the way that we want to do it is a little bit more special, and it's an approach using DIC. So how do we do it? We use a scan of, let's say, computed tomography scan of our material. And by this computed tomography scan, we obtain a set of images on top of each other, which represent the material in 3D. If we apply DIC for each slice, we will get a displacement field, but it's not actually a displacement field. It's more representing the dislocation of each fiber compared to the previous slice. And using this data, we can post-process it and assign these displacement values to each fiber individually. To make it maybe a little bit more clear, so here we have one slice, and in the next slice, we can see that the cross-section of our fiber is moved. And using DIC, we can characterize this change in cross-section position, let's say. And once we have these vectors V and U, using some basic math, we can obtain the orientation of that fiber, which provides us, let's say, fiber orientation distribution for the whole volume. We should note that this is a special application of DIC. As in a typical DIC, we import the images of, let's say, consecutive steps of a deformation. But here in this case, the input images are taken all at one time step. And secondly, the objective of analysis in typical DIC is mechanical deformation. But here in this case, we want to obtain in the end the macrostructural evaluation of the material. This is our specimen, the glass epoxy and also carbon epoxy cross-poly laminate, which was produced using hand layup and autoclaving. We cut it using water jet to a double notch specimen, and we performed a synchrotron computed tomography at SLS in Switzerland. And as you can see here in this cross-section of this material, we can see the fibers quite well. But for the carbon epoxy material, that's not the case. We can somehow see the fibers, but we cannot really define the edges of these fibers. So this is the main difference between these two materials. So these are the results for glass epoxy material. And the last slice I'm showing here, as you can see, the V corresponds to in-plane orientation or in-plane displacement, and V corresponds to out-of-plane orientation. This is the V strain map. And finally, using these two maps, we can assign to each fiber these displacement vectors, which mean that these fibers have this amount of displacement compared to the first slice in the stack. Okay, let's look at one fiber and see if the method works. So in the bottom slice, I choose this fiber, and then I try to locate this fiber in the top slice, and then by, let's say, mapping these two fibers in one coordinate system, I see that there is a little bit of out-of-plane displacement between the two positions, but there is even a higher or larger in-plane displacement for this specific fiber. If we do this with DIC, we can plot this U and V for each slice through this stack. And if we also manually measure this U and V, we see that the numbers that we get, for example, for the last slice, are in quite good match with our DIC results. Now we can look at more fibers, but average. So here I try to plot the average displacement of all the fibers in this volume through the length of the volume. And we see that there is a quite linear increase for this displacement of fibers, which means that the fibers are basically straight. And this I already explained. In this kind of processing, each fiber receives a history, meaning that each fiber has a U and V vector assigned to it in every single stack. We can see that both positive and negative values are detected for U and V, which means that we have misalignment in both directions. And the fibers tend to misalign in clusters. We see some clustering of this displacement features, which means that the neighboring fibers tend to be in one or in let's say, similar orientation. Using the orientation for individual fibers, we can obtain distribution of orientation for the fibers analyzed in that volume. And as you can see here, for in-plane orientation, they don't center around, the distribution doesn't center around 0, but it centers around the value of 2.3, more or less, which means that the sample has a global, let's say, tilt with regard to the scan axis, I would say. And this could be due to the not perfectly aligned, let's say, perfectly alignment during the mounting of the specimen or during cutting of the specimen. But this is something that we can notice, and we can also validate it using Waxtex, which is in-house developed software in our group, which works quite well and efficient, and it gives misalignment or orientation values for voxel-based model, but not for individual fibers. But anyway, we can see a quite good match, I would say, between the results, and that's what makes us happy, of course. But can we skip the last part, which is the post-processing to assign displacement values or misalignment values for individual fibers? By this, I mean, if you look at the results of, look at this dashed line here, this is the results of DIC, but you just apply DIC and you plot the averages of all this displacement map versus the length. And here in this graph, let's say the solid one, which is below this yellow one, the values of individual fibers are averaged. So we can see that there is a small difference between the two, but that's not a huge difference. And this makes us conclude that if we want to skip this post-processing, and if you want to do, because this post-processing part is quite intense in time, so we can skip it and we can just stick to DIC averaging without individual fiber analysis, and we can still trust the results up to a good extent. And this has another advantage, which is the possibility of applying this technique to images where the fibers are not distinctly visible. As you can see here, for this carbon epoxy case, we don't see really the fibers, but still we can use this technique using DIC average results, and we can obtain, as you can see here, strain maps displacement maps for orientation. Okay, that was about it for DIC. Now I'm going to shortly also talk about digital volume correlation, which is a 3D extension of DIC. So the core concept is the same. We have consecutive images of our deformation, and we take these images during loading or in situ loading of the material. But here the difference is that rather than looking at the surface of the material, we acquire 3D volumes using, for example, or mainly computed tomography. And we apply again the same type of correlation to these consecutive images to obtain displacement and strain maps. But here, of course, we need again a speckle pattern, but this speckle pattern is not only needed on the surface, but it should be inside the whole volume. And that's something that makes it sometimes tricky to perform this technique. If you have this type of, let's say, pattern inside your material, thanks to the inherent texture, that's good, you are lucky. If not, then you have to somehow introduce a 3D speckle pattern inside your material, and that's not always straightforward. And on the other hand, it can influence the mechanical properties that you are going to even evaluate during your test. We apply DVC here using Aviso software, in which DVC can be done in two different approaches, local and global. Local or subset-based is actually coarse type of analysis, which provides displacement fields which are not continuous. So you can have discrete displacement fields, but on the other hand, there is a different algorithm for DVC, which is global or finite element based, and there it assures the continuity of the displacement results. Of course, this approach is used as a rough or, let's say, basic analysis because it's very efficient, it's not too time consuming, and then the results of this can be fed into global DVC in order to guide the algorithm better. But of course, these algorithms are quite time consuming and computationally heavy. Sometimes it's not possible to run this type of analysis on your own PC, even if it's a very strong one. The specimen here that we studied is, again, similar to what I just showed in previous slides. It's specimens prepared by the fiber mode guys that they did most of the time a lot of fiber break analysis on this type of a specimen. But here in this case, we want to look at the damage, basically transfers, matrix cracks, and delamination in such a specimen. So during the scan of the specimen inside synchrotron, we apply tension to the specimen and we look at this tiny region via synchrotron computed tomography. Again, similarly, if you want to evaluate how DVC works using our fiber texture, because here we didn't introduce any speckle pattern in this case, in order to evaluate how the fibers can act as speckle patterns, we did a similar study. We applied digital deformation, and we had to look at two different plies, transverse plies and longitudinal plies, because as you can see, the images are quite different depending on the angle the ply makes with your beam. And the results are, or some of the results are shown here. In this case, as you can see that the deformation is recognized by DVC, the virtual deformation of 2%. In the strain fields, you can see some, how to say it, some strips, which are attributed to the fact that digital deformation is not conducted uniformly on the image. There is some, let's say, heterogeneity due to interpolation during this digital deformation. And we also induced a crack, again, digitally in the region of the volume of interest. And we can see that in some cases, the crack is very well detected. In some cases, less quality, and that corresponds to the direction of the fibers. So once we have, I think, a crack which is perpendicular to the fibers, it's not very easy to detect it due to the fact that we don't have enough pattern for the DVC to track this deformation along the fibers. Another thing that we should consider during DVC is that on the edges, we always have some edge effects, if you want to call it like that. And you can see that this high localization of a strain happening on the edge. And it's important to exclude these elements on the surfaces if you want to have better results. As you can see here, these results look much more uniform as they should be. And this is the heterogeneity that I just talked about coming from the digital deformation, and also looking at the mesh element size. Here we can see that once we go for lower, let's say, elements, we get more variation detected by DVC. Again, we can look at the, here I want to just briefly talk about the size of this crack. As you can see here, once we have a 1 pixel crack, it's detected quite well. And if we increase the crack size up to some extent, we see that it's detected quite nicely. But when we go, for example, to a value of 32, that's not the case anymore. And this means that once we go above, or once we exceed the element size with DVC, we are not anymore able to characterize accurately the crack, which makes sense. And here it's the other way around. I keep the crack size constant, and I just increase the element size, and we see that for all element sizes, the detection is quite well. But of course, with the smaller elements, the accuracy would be higher, as long as you have enough speckles inside your elements. So once we have done that, now we are ready to apply DVC to real deformation images. And we start with such a volume. And these are the steps on the low displacement map, which I have chosen, on which I have chosen the volumes of interest. This is the results of the local or subset-based DVC. We can see that here in this transverse ply, the first transverse crack is detected. And once we continue the loading, a form of delamination appears here at this transverse crack. and then some apparently fiber splitting are visible. And going on, we can see that two other transverse cracks form at the other transverse ply, and so on, until a moment that we see that the cracks or the damage in general is disappearing, which is not in reality the case. But it's just because, as I already mentioned, once the crack becomes too large or larger than your analysis, let's say, grid, then it's not able to follow it anymore. Then we choose a smaller region of interest or volume of interest to save some computational costs to perform global DVC or finite element based DVC. And here we have a tetrahedral mesh of something around 18 micrometers. Let's look at the results. We see that transverse crack shows up here in the transverse ply, and it grows, it propagates during the specimen loading, and then we have some delamination appearing at the just at the interface between the 0 and 90-degree ply, with some fiber splitting, of course, in the 0-degree ply. And again, we have somehow the loss of, let's say, damage detection by a DVC due to too large damage features. We can visually check if the features that are detected here correspond to real features. And as we can see, this transverse cracks is present there. So DVC has detected correctly that transverse crack, and also the fiber splitting, which is shown here, is also well detected. To look at the delamination, I don't know, maybe you can see something here as sort of delamination. So the three features that we have detected via DVC, via global DVC, actually correspond to real features and are correctly detected. And finally, I said too many times finally, but this is really finally, we are now applying this DVC methodology in the HyFiSyn project in order to obtain the, let's say, interfacial properties, or in order to, let's say, have a better characterization of the longitudinal debonding of the fiber and matrix where the fiber breaks. And here in this case, as you can see, we have introduced nanoparticle in our matrix, which was also a challenge to obtain, especially since you have to solve it in your resin before the impregnation. And that's something that the HyFiSyn guys here at KU Leuven are working on, and we are getting there. So please stay tuned for this. And with this, I want to thank you for your attention, and also the colleagues who were involved. Thank you.